All right, let's continue on with Chapter 4, the Bernoulli equation and pressure variation. In this recording, we're going to derive Bernoulli's equation, section 4.6. And we're going to do this along a streamline. We'll derive an equation, and then we'll see that it's a very useful equation. In the next video, we'll talk about 4.7 and apply this for making pressure measurements within flow. So let's go ahead and skip forward here to section 4.6. And let's start the derivation. The key assumptions that we need to make are that we're going to do this derivation along a streamline that allows us to use the equations for velocity and acceleration that we've talked about before. We're also going to assume, and this is very important, we're going to assume steady flow. That means that the velocity field is a function of position only. Remember, S is our position along a streamline, and that could be, or at least S is a position vector. It could be a function of X, Y, and Z in 3 dimensions. So it's important to note that it is not a function of time. This will be steady flow, and the partial derivative of v with respect to time will be equal to 0. And therefore the local velocity will be, or I'm sorry, the local acceleration will be 0. It's also inviscid flow, so we're assuming there's no viscous effects, there's no resistance to the flow. And we're also going to, in deriving this equation, we're only going to calculate the flow that's tangential. So we'll only be dealing with this vector right here. So we will not be considering the normal vector. So to derive this, we set up our normal equation. The partial derivative of the piezometric pressure with respect to position, or S, along the streamline. The negative of that, remember basically the pressure is going to be, the pressure gradient is going to be in the opposite direction as the acceleration. And so on the other side of the equation, we have rho times the acceleration in the tangential direction. And since it's only in the tangential direction, and we know that the local acceleration, del v del t, is 0, then this just becomes v del v over del s. So we can plug that into the equation here, and that's easy enough to do. We plug for alpha, for the tangential acceleration, we plug in this value to here, and it becomes in this case it becomes, since v is only a function of s, we can make this a full derivative, dv ds. And we also note that ds of v squared over 2 is equal to v dv ds. So this is right here. This is kind of the crux of the derivation here. This is the important step in the derivation to make this connection between these two derivatives here, or these two terms, and note that they're equal. So what we can do then is, because we've written this now as d ds of this quantity, we can move rho v squared over 2 into this integral on the left-hand side, and we can basically multiply through by -1. This is looking very, very similar to the equation that we had before when we talked about piezometric pressure and piezometric head, except we have an extra term now. This is called the kinetic pressure. Note that these, to have dimensional homogeneity, all of these terms have to have units of pressure. And so this is called the kinetic pressure. And as before, we can differentiate this, and we will see that the left-hand side is basically equal to a constant. And this is the same sort of situation that we had before when we were dealing with piezometric pressure and piezometric head. So if this is equal to a constant, then anywhere in the fluid, this quantity, the pressure plus gamma z plus the kinetic pressure, basically the piezometric pressure plus the kinetic pressure, is going to have to be conserved. And so we can choose two places along a streamline as long as we're on the same streamline. Remember, we derived this equation on a streamline. So as long as we're on the same streamline and we're not jumping across to another streamline, this equation will hold for 2 points along that streamline. We can also divide through, as we did before with piezometric head, we can divide the equation through by gamma, and now all the terms have units of length. Um, and um, and so we can see that this is the familiar piezometric head here, and then we have this velocity head term. So we can summarize these equations in table 4.3. We've got the Bernoulli equation in head form here at two locations along a streamline. We're going to have, we can see that now we have ones on all these locations because this are all these variables, all these terms, because this is the equation at point 1 and point 2 along the streamline. As before, we have the static pressure, and then we have gamma, which is the specific weight. V is now the speed of the flow tangential to the streamline, and G and Z are just the gravitational constant and the elevation. And if we multiply through by gamma, as we saw before, if we multiply through, we have the pressure form of Bernoulli's equation. And we now can see that we also have, I should also mention that P over gamma here, this term here, is called the pressure head. And so this term here is the velocity head. P over gamma plus Z is the piezometric head, which we saw before, and P plus gamma Z is the piezometric pressure. This term plus this term. Remember that rho G is gamma. This is the pressure, the piezometric pressure, as is P2 plus rho G Z2. That's the piezometric pressure at point 2. And then we have this kinetic pressure, which I defined here in the previous slide. So we now need to learn how to apply these equations. So what we see here is if we have a couple of different ways of interpreting this, and one is to think about how this quantity, the total head, is being conserved along the streamline, and we can think of that kind of in an energy sense, where we have these three terms: the elevation, the pressure head, and the velocity head, all adding up to some quantity. But since this is conserved at point 1, point 2, and point 3, these different quantities may change. We can see that the elevation has gone up a little bit, the pressure head has gone down a little bit, and the velocity head has increased a little bit. But all the time we're maintaining the same amount of total head. Now at point 3, again, this is all along the same streamline. At point 3, the elevation is even higher. The pressure head has gone up a little bit because this is expanding a little bit, and the velocity head has to decrease because of that. So we can see that the piezometric head and the velocity head kind of trade off here. In this case, because in this case we can see that Z3 plus P3 over gamma is the same as Z1 over P1 over gamma. This is at the same elevation, and so the velocity heads have to be the same. So what we note now is that the velocities V1 and V3 must be the same, because that's the only thing that's changing here to create the velocity head. So at points 1 and 3, since the velocity is the same, then the piezometric head must be the same. So these things have to be conserved. The other alternative is to think of this as kind of velocity and piezometric pressure varying inversely. So when one goes up, the other goes down. So we can rewrite this equation now in terms of piezometric pressure. We note that the piezometric pressure plus the kinetic pressure has got to equal a constant. And so since this is constant, if the velocity increases, the piezometric pressure has to decrease. If velocity increases, I'm not sure how I said that. If this decreases, this has to increase. If this increases, this has to decrease. So they have to go, if one goes up, the other has to go down, and vice versa, in order to keep the quantity constant. So this is a very convenient way to look at flow in moving fluid in some sort of a pipe. And as long as we identify an appropriate streamline, and usually the best way to do this is to choose the center line of a pipe, then we can realize that the total head or the total pressure is going to remain constant throughout the entire flow, as long as we're on a streamline. So that's it. I will have another video to do this example, and the next video will discuss how we use the principle of Bernoulli's equation to measure velocity and pressure in a pipe.